Okay guys, when we have a positive charge and another negative charge, if they have the same magnitude and if there is a distance between them a or 2a, what it doesn't matter, we call that arrangement an electric dipole. So electric dipole means we have a positive charge and the same magnitude, an electric charge of the same and another negative charge of the same magnitude, and there is some distance between them. So that arrangement here, we call it an electric dipole. If we need to find what is the electric field from an electric dipole, positive charge and negative charge, at some distance x on the axis between them, this is a very easy problem. That's not hard. So what we're going to do is, at that point, at point x, at that point, the electric field from the positive charge Q, it's going to be along that direction, right? And the electric field from the negative charge Q, it's going to be, Lena? It's going to be along that direction. Am I right? Right? Yes. Good. Can you tell me why is it along that direction? Not because it's a negative charge. So it has to be into the charge. And if you look at those two electric fields, if you resolve them into two components along the x and the y axis, you will find out that the only surviving component is the component along the y axis, the negative y axis. And the two components along the x axis will cancel out. So from that electrical dipole, at any point along that line of symmetry, the electric field will be along the negative y-axis for that arrangement. Can we calculate that total electric field? Let's find out. The electric field E from charge number 1, is going to be K, Q, divided by that distance squared, R squared. So it's going to be K, Q, divided by the distance squared. This is the electric field E. The component of that electric field along the negative y-axis, we have to multiply by the sine of that angle theta. So that's the electric field along the negative y-axis is going to be K, Q, K, this quantity is K, Q divided by R squared times sine theta. Then multiplied by 2 because we have two charges, so I'm taking into consideration the other charge Q, negative Q. Then we have to multiply that quantity by 2. And the negative sign, because it's along the negative y-axis. So now we have everything, every single information is given in here. K, Q over R squared, this is the electric field. Multiplying it by sine theta, that means that we have only the components along the y-axis. And negative sign because it's along the negative y-axis, and the 2 because we have a positive charge and negative charge. We have two charges. So this is the electric field from that electric dipole. That's it. We can simplify that a little bit further by putting the value for R squared, which is going to be x squared plus a squared. If I call this a, and that's x, then R squared is going to be x squared plus a squared. That's it. And sine theta, if you replace it by a over r and put the value for r, you get this long formula for the electric field from an electric dipole along the line of symmetry. So this is the equation that describes to us the electric field from electric dipole along the line of symmetry. This is, of course, do not memorize that. That's a very straightforward problem if it comes in the exam. But we want to examine this a little bit further. If you look at that equation, and let's assume that the distance between the two charges is much smaller than the distance x. So those are the two charges, and you're calculating the electric field very far away. We call that the far field. So if you calculate the electric field in the far field, am I right? I'll go back. That means, guys, A is much smaller than x. So we can ignore that a squared in here. So you end up having 2 minus 2 times k times qa divided by x squared to the power of 3 over 2. You just ignore that a square, because if you have 1000 squared plus 1 squared, that 1 squared will not do anything. It's a very small value. So this is a small value in here. So if we just ignore that. In the far field, we just ignore that part. And that's what you get. Oops, sorry. Am I right? Yes. In the far field, oh, oops. Okay. The electric field will proportional to 1 over x cubed. It's going to be k minus 2k qa divided by x to the power 3. Oh, it's proportional. It's not equal to. I'm just giving you the function. So the electric field is going to be some constant, which is, that constant is going to be minus 2k qa divided by x cubed. So the electric field is going to be proportional to x cubed. This is in the far field. Okay, if we look at the electric field between, if we draw the electric field from those electric dipole from two positive charges, two similar charges. This is going to be the, if you have two positive charges and you put them closer to each other, the electric field from those two arrangements is going to be something like this. In the area between them, you will have a point that has a zero field. And you can explain that. Can you explain that to me? Sharif? Electric field lines. Sharif is saying, well, you will have an along the line between the two charges, you will have an electric field going from charge number 1 going along that direction, and from charge number 2 going along that direction. So at some point, those two electric fields will be equal in magnitude. At some point, will be equal in magnitude, and they will cancel each other. That's why you got a zero between the two charges. Zero electric field somewhere between the two charges. Look at that problem in here. If you have a ring that has some charges on it, positive charges in it, and we need to find what is the electric field exactly at the origin. What is the electric field exactly at the center of that ring? Guys, can you just discuss that together? Can you discuss it with your colleague for 2 or 3 minutes? Then we'll vote on the answer. We'll choose one of the 3 answers. We need to find the electric field exactly in the center of that ring. Now discuss it with their colleague, then we'll vote on it. Maureen, do you know the answer? Okay. You can reach it mathematically, and you can reach it actually by intuition. Yeah. And I need anything. I need just an explanation. Why did you reach that answer? It doesn't matter. As long as it's correct, I'm okay with it. Can we vote? Okay. Who's in for A? 0. Who's in for B? and C. And there's nothing else, guys. I see people did not raise their hands at all. You have to choose an answer. You have to choose an answer. And you have to base it on some information, some explanation. Okay? I forgot your name. Sharif. Why do you think the answer is B?
Q will be equal to 2 pi r lambda.
Q will equal to 2 by r lambda. Electric field equals to K Q over R squared. Sharif is saying, well, the electric field will equal to K Q over R squared, and this is valid for anything. This is what he says. Since he applied to that case, that means that this is valid for anything. If this is true,
No.
why not?
Because, yeah, it applies to everything, but in this case, if you take opposite segments of
No, I didn't ask you to solve. Does this equation apply for any charge distribution? Okay, then for this charge distribution, what is the electric field? It has a charge Q on it. What is the electric field? What is the electric field at that point? Well, according to you guys, K, Q divided by R squared. What is R squared? What is R squared? The distance. What distance? From which point from the charge?
to the point,
This, this, which one is R? So this is not what I'm supposed to do. What I'm supposed to do is the electric field will gonna equal to, I take a small part in here and say that the electric field from that small part equal to K dq divided by R squared, then do the integration from the beginning of the shape to the end of the shape. And of course, because this is a really hard shape to deal with, we cannot solve that one. We can solve it, but it's not that easy to do that integration. It's out of the scope of the course. So again, this is a valid equation for only for a point charge. If I know the exact location of that charge, and this is valid only for a point charge. So we cannot use that equation in that case because we have a charge distribution. What we have to do is divide that ring into small segments. Each one will carry a charge dq. Find the electric field from that small segment and do the integration. And this is how can we reach it mathematically. And you get an answer. You will get an answer. I forgot your name, Abdullah. But Abdullah, actually, he was giving me a hand. He was saying, I will let you answer that, Abdullah.
okay, if we take opposite segments
Okay.
in the circle,
Okay.
and then find the resultant force,
Mhm.
will be zero.
Okay.
The resultant electric field
Okay.
will be zero. And if we go around the circle, it
Mhm.
will be zero. And mathematically speaking, the area between the curve and the x-axis, below and above the curve, are going to cancel each other out. So the integration of this is going to be zero.
So Abdullah is saying, I'm going to talk about the first part, not how to do it mathematically, complete mathematically. Abdullah is saying, if we have a ring, and if you need to find the electric field exactly at the center, then I'm going to choose a segment in here, and it will have at that point it will have an electric field along DE, and I choose a similar segment on the opposite side, and it will have an electric field DE. If you look at those two electric fields,
Minus D
they will be equal in magnitude, opposite in direction. They will cancel out. The electric field from those two segments equals to 0. Then I'm going to choose a segment here and another one in here. The electric field from those two segments is also 0. The total electric field from those segments. And if you keep on doing this, each two opposite segments will give you an electric field, a net electric field of 0. So that's what Abdullah said. So now we have listened to the explanation of Sharif, and we have the explanation for Abdullah, and no one has chosen that as an answer. So which one is the correct one? A. So we don't even need to go on and solve it mathematically and do the integration, though we can do it. We did last time. Last time in class we did that, right guys? And we have agreed to integrate from the beginning to the end, and the integration was something like from 0 to 180 or from 90 to 100 to 270, it doesn't matter. So if you complete that ring, the integration will be from 0 to 360, and that integration for sine theta d theta will give you 0. I don't want to go solve that problem again because we solved it last time. But it's exactly the same thing that we have done for the semicircle one. But instead of having the integration from 0 to 180, we'll do the integration from 0 to 360, and that integration will give you 0. 0 multiplied by a constant will give you 0. But I'm just trying not to go over it again, unless you want me to.
Yeah, I understood this. Last time when we did to get the sine theta, we had the only vertical.
No. We after we did the straight line, the infinite straight line, we did the semicircle. Right, guys?
Yes.
I solved the semicircle in class.
This is not my question. To get the sine into integration, we drew a line like this.
Yes.
The dx.
Yeah, I said that we're going to have you're going to do exactly the same thing. You're going to take a segment that has a length of dx, that has a charge dq, and you'll find that segment will make an angle here d theta, and this angle is theta. That segment is at an angle theta from that line. Okay? Then you'll say the electric field from that segment is going to equal to k dq over r squared. Replace dq by its value, that's lambda dx. Replace dx by r d theta, and take only the component that will not cancel out for that semicircle. Another component.
In the circle, that's my question. There will be no component that will cancel.
Then you will do it for the two components, and you still get a 0. You still get a 0. Okay, guys. But the simplest solution without going into much mathematics is by symmetry. So by symmetry, we can find that the electric field inside at the center of this is equal to 0. As a matter of fact, and we'll prove that in a few minutes, the electric field everywhere inside that ring is equal to 0. And we'll see how. I'm going to skip that part, and I'm going to go straight to chapter 24.